calculation of inversion temperature, calculation of work done in reversible isothermal process and calculation of work done in irreversible isothermal process. In continuation, today we are going to discuss adiabatic expansion of an ideal gas, comparison between isothermal and adiabatic expansions, work done in adiabatic reversible expansion, thermochemistry, exothermic reactions, endothermic reactions and heat of reaction or enthalpy of reaction. First, let us discuss what is adiabatic process. The process carried in a vessel whose walls are perfectly insulated, that is, no heat is exchanged through the walls of the vessel, then the process is called adiabatic process. In an adiabatic process, no heat is exchanged between the system and the surroundings, hence Q is equal to 0. By first law, you know that delta E is equal to Q plus W. For adiabatic process, Q is equal to 0, hence W will be equal to delta E, or we can say decrease in internal energy will be equal to work done. As the work is done on the expense of internal energy, hence internal energy decreases during the work done in adiabatic process. Let us consider 1 mole of the gas at pressure P and at volume V. For an infinitesimal change of volume which is equal to dV, work will be equal to minus P dV. Then for adiabatic process, W is equal to delta E, hence dE will be equal to minus P dV. By the definition of heat capacity, you know that dE is equal to Cv dt. Hence, putting the value dE equal to Cv dt, we will get Cv dt equal to minus P dV. Here Cv is the heat capacity at constant volume. For ideal gases, you know that for 1 mole of the gas, PV is equal to RT, or we can say that P is equal to RT by V. Putting the value of P in the given equation, we will get Cv dt equal to minus RT dV divided by V. Rearranging this equation, we will get Cv dt by T equal to minus R dV by V. Integrating this equation between the limits T1 T2 and V1 V2, we will get Cv integral of dt by d in the limits T1 and T2 equal to minus R integral of dV by V in the limits V1 and V2. We will get Cv natural log T2 upon T1 equal to minus R natural log V2 upon V1. As you know that R, that is universal gas constant, equal to Cp minus Cv, means the difference between the heat capacities at constant pressure and the heat capacity at constant volume. Hence, putting the value of R equal to Cp minus Cv, we will get natural log T2 by T1 equal to minus Cp minus Cv upon Cv natural log V2 divided by V1. The ratio Cp by Cv is known as Poisson's ratio and is denoted by gamma. Hence, putting the value of gamma to be equal to Cp by Cv, we will get natural log T2 by T1 equal to minus gamma minus 1 natural log V2 by V1. Replacing the negative sign, we will get T2 by T1 equal to V1 divided by V2 whole to the power gamma minus 1, or we can say that T2 V2 to the power gamma minus 1 equal to T1 V1 to the power gamma minus 1. From this, we can say that T multiplied by V to the power gamma minus 1 is constant. We can also eliminate temperature by using the ideal gas relationship PV is equal to RT. Hence, putting the value of temperature, we will get T2 upon T1 equal to P2 V2 upon P1 V1. Hence, T2 upon T1 will be equal to V1 upon V2 whole to the power gamma minus 1. This is denoted by equation number 6. Now, equating the right hand sides of equation 5 and 6, we will get P2 upon P1 equal to V1 upon V2 whole to the power gamma. Rearranging, we will get P1 V1 to the power gamma equal to P2 V2 to the power gamma, or it can be said that P into V to the power gamma is constant. Isothermal expansion and adiabatic expansion can be compared with the help of Boyle's law relationship. Boyle's law describes pressure-volume relationship for an ideal gas in isothermal conditions. This relationship is identical to the relationship derived for adiabatic expansion. According to Boyle's law, pressure into volume is constant at constant temperature for constant amount of the gas. But for an adiabatic change, PV to the power gamma is constant. The difference between the isothermal and adiabatic expansion is that in isothermal expansion, temperature remains constant, but in adiabatic expansion, temperature decreases. In isothermal expansion, heat is absorbed to make up for the work done by the system in expansion. But in adiabatic expansion, work is done at the cost of internal energy, which decreases the temperature. This is the reason because of which the pressure volume curve for adiabatic expansion is steeper than the pressure volume curve for isothermal expansion. You can have a look on this graph for isothermal expansion and adiabatic expansion for ideal gas. This graph is made for monoatomic gas. For monoatomic gas, value of gamma is equal to 1.67. You can see that slope for adiabatic expansion graph is greater than the slope for isothermal process. This is because of the difference in relationship. For isothermal expansion, PV is equal to constant, and for adiabatic expansion, PV to the power gamma is equal to constant, and gamma has a value greater than 1. Now, we will derive a relationship for work done in adiabatic expansion of ideal gas. You know that for an adiabatic process, PV to the power gamma is constant. Differentiating it, we have gamma PV to the power gamma minus 1 dV plus V to the power gamma dP is equal to 0. Dividing whole of this equation by V to the power gamma minus 1, we will get gamma into P dV plus V dP equal to 0. Therefore, V dP will be equal to minus gamma multiplied by P dV. You know that for 1 mole of the ideal gas, PV is equal to RT. So, putting this value, we will get P dV plus V dP equal to R dt, that is V dP equal to R dt minus P dV. This is given as equation number 8. Substituting the value of V dP from equation number 7 and 8, we will get R dt minus P dV equal to minus gamma P dV, or we can say that R dt equal to P into 1 minus gamma dV. Rearranging, we will get P dV equal to R dt upon 1 minus gamma. If there are n moles of a gas, this equation will change to the equation P dV equal to nR dt upon 1 minus gamma. Now, integrating in the limits T1 V1 to T2 V2 with taking gamma as constant, we will have minus W equal to P dV, which is equal to integration of nR dt upon 1 minus gamma within the limits T1 and T2. This will be equal to Nr multiplied by T2 minus T1 upon 1 minus gamma, or we can say that W is equal to minus Nr multiplied by T2 minus T1 upon 1 minus gamma. As the value of gamma is greater than 1, hence 1 minus gamma will always be negative. If T2 is greater than T1, then T2 minus T1 will be positive and work done will be positive. This means this is the work done on the system and this is the work of expansion. On the other hand, if T1 is greater than T2, then T2 minus T1 will be negative and work done will also be negative. This means this is the work done by the system and this is the work of expansion. Now, let us discuss an example to understand the work done in adiabatic expansion. Calculate the work done for the adiabatic reversible expansion of 2 moles of an ideal gas at 273.2 Kelvin and 20 atmospheres to a final pressure of 2 atmospheres. Given that Cp is equal to 5R by 2 per mole per degree, Cv is equal to 3R by 2 per mole per degree, and universal gas constant R is equal to 8.314 joule per mole per degree. To calculate work done, we have to calculate the final temperature T2 first. To calculate the final temperature, we have to use the relationship T2 upon T1 to the power gamma equal to P2 upon P1 to the power gamma minus 1. As you know, the gamma is equal to Cp by Cv and both the values Cp and Cv are given. Hence, gamma, that is Poisson's ratio, will be equal to 5 by 3. Putting the value of gamma in the given equation, we will get T2 upon 273.2 to the power gamma, that is 5 by 3, is equal to 2 upon 20 to the power gamma minus 1, that is 2 upon 3. Solving it, we will get T2 is equal to 108.8 Kelvin. Now, to calculate the maximum work done, W is equal to minus Nr multiplied by T2 minus T1 upon 1 minus gamma. Putting all the values here, N equal to 2, R equal to 8.314, T2 equal to 108.8 Kelvin, T1 equal to 273.2 and gamma equal to 5 by 3. We will get minus 2 multiplied by 8.314 multiplied by 108.8 minus 273.2 divided by 1 minus 5 by 3. Solving this, we will get W is equal to minus 4100 joules, which is equal to minus 4.1 kilojoules. There is an alternative method to calculate the work done in adiabatic expansion. As you know that Q is equal to 0 for adiabatic expansion, hence W will be equal to delta E, and delta E is equal to NCV dt. Therefore, work done for adiabatic expansion will be equal to NCV T2 minus T1. You have already calculated the value of T2 for adiabatic expansion, which is equal to 108.8 Kelvin. Putting the values of N, Cv, T2 and T1, we will get the work done for the adiabatic expansion. Therefore, W will be equal to 2 multiplied by 3 by 2 multiplied by 8.314 multiplied by 108.8 minus 273.2, which is equal to minus 4100 joules, which is equal to minus 4.1 kilojoules. Let us derive an expression for the work done in irreversible adiabatic expansion. If the irreversible adiabatic expansion is free expansion, then external pressure will be equal to 0. As the work done is minus P external dV, hence the work done will be equal to 0. As you know that for adiabatic expansion, Q is equal to 0 and from first law of thermodynamics, delta E is equal to Q plus W. Here Q is 0 and W is also equal to 0, hence delta E will also be equal to 0. As delta H is equal to delta E plus work done, hence delta H will also be equal to 0. Therefore, for free expansion, which is adiabatic irreversible free expansion, W, Q, delta T, delta H and delta E equal to 0. For intermediate adiabatic expansion, W will be equal to minus P dV, that is W will be equal to minus P multiplied by V2 minus V1. Therefore, W will be equal to minus P external multiplied by R T2 upon P2 minus R T1 by P1, which is equal to minus P external T2 P1 minus T1 P2 upon P1 P2 multiplied by R. As W is also equal to CV multiplied by T2 minus T1, therefore, CV multiplied by T2 minus T1 will be equal to minus R multiplied by P external into T2 P1 minus T1 P2 upon P1 P2. Now, we are going to discuss an important branch of thermodynamics, which is known as thermochemistry. Thermochemistry deals with the energy changes during chemical transformations or chemical reactions. Thermochemistry is also known as chemical energetics. Thermochemistry is based on first law of thermodynamics. Chemical reactions are accompanied by absorption or evolution of heat energy. When reactant molecules are converted to product molecules, there is rearrangement of energy. The bonds in reactant molecules are readjusted to form the product molecules. The chemical bonds in reactant molecules are broken up and these bonds are formed to make the product molecules. The heat energy is used up during the bond breaking and the heat energy is released during the bond formation. There are two types of thermochemical reactions based on energies. These are exothermic chemical reactions and endothermic chemical reactions. First, we are going to discuss exothermic reactions. Heat is evolved out in exothermic reactions. This happens when the sign of delta H is negative. It can happen only when the bond energies of reactant molecules is less than the bond energies of product molecules. We can say that for exothermic reactions, delta H is equal to negative, that is enthalpy of products minus enthalpy of reactants is negative, or it can be said that enthalpy of products is less than the enthalpy of reactants. The second type of thermochemical reactions are endothermic reactions. Heat energy is absorbed in endothermic reactions. It is possible only when the bond energies of reactants is greater than the bond energies of products. The sign of delta H for endothermic reactions is positive, that is Hp minus Hr, that is enthalpy of products minus enthalpy of reactants is positive. It can be said that enthalpy of products is greater than enthalpy of reactants. If we are considering at constant volume, then delta E is equal to E of products minus E of reactants, which will be positive. It can be said that internal energy of products is greater than internal energy of reactants. You can have a look on sign conventions for Q, E and H, that is heat change, internal energy change and enthalpy change. For exothermic reactions, all are taken to be negative and for endothermic reactions, all are taken to be positive. There is an example for the representation of exothermic reaction. An exothermic reaction can be represented as aqueous NaOH plus aqueous HCl giving you aqueous NaCl plus liquid water plus 13.7 kilocalories, or you can write the exothermic reaction in the way aqueous NaOH plus aqueous HCl giving you aqueous NaCl plus liquid water, and delta H is equal to minus 13.7 kilocalories. Consider another example for the representation of endothermic reaction. Solid carbon plus gaseous water gives you gaseous carbon monoxide plus gaseous hydrogen minus 31.4 kilocalories, or you can write this equation as solid carbon plus gaseous water gives you gaseous carbon monoxide plus gaseous hydrogen and delta H equal to plus 31.4 kilocalories. Let us discuss the heat of reaction or enthalpy of reaction. Heat of reaction or enthalpy of reaction is defined as the heat absorbed or evolved when the given amount of substances, that is reactants, by a chemical equation are completely reacted. It can also be said that heat of reaction is the difference in heat energy or enthalpies of products and reactants when the given amounts of the chemical reactants given by the chemical equation are completely reacted. Mathematically, enthalpy of reaction is equal to delta H, which is equal to sum of the enthalpy of products minus sum of the enthalpy of reactants. For example, if an equation is given as gaseous hydrogen plus gaseous chlorine gives you gaseous HCl plus 44.0 kilocalories, or delta H equal to minus 44 kilocalories. This reaction shows that 2 grams of hydrogen, that is 1 mole of hydrogen, and 71 grams of chlorine, that is 1 mole of chlorine, completely reacts to give 73 grams of HCl, that is 2 moles of HCl, and the heat evolved is 44 kilocalories. Hence, this reaction is exothermic and reacting system loses 44 kilocalories of heat. It can also be said that enthalpy of the system decreases by 44 kilocalories. Let us have a look on another example. C2H4 gaseous plus 3O2 gaseous gives you 2 CO2 plus 2 H2O. Here delta E is given to be minus 335.8 kilocalories. As the value of heat is given at constant pressure, that is delta E is given, hence this equation shows that 1 mole of C2H4 reacts completely with 3 moles of oxygen to give 2 moles of carbon dioxide and 2 moles of H2O and minus 335.8 kilocalories is evolved at constant volume. This reaction is also an exothermic reaction and the reacting system loses 335.8 kilocalories heat at constant volume. If heat of reaction at constant pressure is given, then we can calculate the heat of reaction at constant volume. Let us have a look on an example. At 25 degrees Celsius for the combustion of 1 mole of liquid benzene, the heat of reaction at constant pressure is given by liquid benzene plus 7.5 gaseous oxygen gives you 6 carbon dioxide gaseous plus 3 H2O liquid, and delta H is given as minus 780,980 calories or 780.980 kilocalories. What would be the heat of reaction at constant volume? You know that delta H is equal to delta E plus delta N RT, where delta N is the difference in number of moles of gaseous products and reactants. Therefore, delta N is equal to 6 minus 7.5, which is equal to minus 1.5. Therefore, delta E will be equal to delta H minus delta N RT, putting the value of delta H equal to 780,980, delta N minus 1.5, R equal to 2 calories and T equal to 298 Kelvin. We will have delta E equal to minus 780,980 plus 894, which is equal to minus 780,086 calories or minus 780.086 kilocalories. Let us revise the topics which we have learnt today. Adiabatic expansion of ideal gas, comparison between isothermal and adiabatic expansions, work done in adiabatic reversible expansion, thermochemistry, exothermic reactions, endothermic reactions and heat of reaction or enthalpy of reactions. In continuation, in our next lecture, we will discuss the factors affecting heat of reaction or enthalpy of reaction.